Picture this. You're at a drag strip in 1981, sitting in your meticulously prepared race car. You spent thousands on the engine, transmission, suspension. You've practiced your launches for years, perfecting your footwork on the brake and throttle. Your reaction times are consistently in the 0.904 range. Elite level stuff. Then some kid from Florida pulls up next to you in a car that's slower than yours by 0.2. The Christmas tree lights start dropping. Yellow, 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 green. Before your foot even lifts off the brake, his car's already gone. He cuts a perfect reaction time while you're sitting there with the respectable, but now completely useless number. You lose. Again and again and again. What the hell just happened? You just got beat by a 17-year-old kid's $40 invention that would completely revolutionize drag racing forever. This is legacy motoring, and I spend way too much time thinking about drag racing history and the engineering breakthroughs that nobody talks about anymore. If you're someone who loves understanding the mechanical genius hiding underneath motorsport's biggest moments, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now look, before we get into the nuts and bolts of how this thing actually worked, I want you to understand something important. This isn't just a story about a clever modification to an automatic transmission. This is a story about a fundamental shift in how human beings interface with machines in competitive motorsport. This is the story of Frank Manzo and the trans brake, a stupidly simple modification that turned bracket racing on its head and made every professional racer's carefully honed launch technique obsolete virtually overnight. Let me set the stage here properly. It's 1980 and bracket racing is absolutely exploding across America. Unlike heads-up racing where the fastest car simply wins, bracket racing is entirely about consistency and reaction time. You dial in your predicted elapsed time before the race, and if you run faster than that dial-in, you're disqualified. This means a 14-second street car can legitimately beat a 9-second race car if the driver is more consistent and has better reaction times. It's the great equalizer of drag racing, where skill and judgment matter far more than raw horsepower and cubic inches. But here's the thing about reaction times in 1980. The absolute best foot brake racers in the world, guys who had been doing this for decades, could maybe on their very best day cut a .020 reaction time. Most really good racers were happy with anything consistently under 0060. The physical limitations of the human body meant there was a hard ceiling on how fast you could release the brake and transition to the throttle when that green light illuminated. You had to see the light, process the visual information, send the electrical signal from your brain down to your foot, physically move that foot from brake pedal to throttle pedal, and then wait for the car to actually begin moving. All of that takes time. Precious hundredths of a second that in bracket racing absolutely determine who wins and who loads their car onto the trailer and drives home empty-handed. Here's what most people don't realize about those reaction time limitations. According to research published in sports medicine journals studying professional athletes, the minimum human reaction time to a visual stimulus, even for elite-level trained competitors, is roughly 150 milliseconds under perfect laboratory conditions. That's 0.150 seconds in drag racing terms, and that's just the time from seeing the light to beginning the movement. Add in the mechanical delay of actually moving your foot and the car beginning to respond, and you're realistically looking at a best case of around 0.040 to 0.060 for truly exceptional racers. The human body has a ceiling, and that ceiling was deeply frustratingly real for everyone competing in bracket racing in 1980. Enter Frank Manzo, a 17-year-old bracket racer from Florida who was sick and tired of losing races because of reaction times. Manzo wasn't some professional racer with corporate sponsors and a massive development budget. He wasn't affiliated with any major racing team or transmission manufacturer. He was just a kid who loved drag racing deeply, understood how automatic transmissions worked at a fundamental level, and had an idea that seemed almost too simple to actually work. What if instead of trying to perfect the impossible task of instantaneous foot movement, you could hold the car completely locked in place while at full throttle, then release it electronically the precise instant the light turned green? The concept was brilliant in its simplicity. Manzo figured out that if you could engage both first gear and reverse simultaneously in an automatic transmission, the transmission would lock absolutely solid. The forward clutch packs would be trying to drive the car forward while the reverse clutch packs simultaneously tried to drive it backward. The result when these forces perfectly oppose each other? The car goes absolutely nowhere, even at wide open throttle with the engine screaming. Then, when you release the reverse clutches, all that stored energy launches the car forward with incredible violence and immediacy. The engine has already been building power against the converter while the car sits motionless. When the lock releases, everything happens at once. Now, you might be thinking, wait, wouldn't simultaneously engaging forward and reverse gears just destroy the transmission immediately? And that's exactly what everyone said when Manzo first started talking about this idea. That was the conventional wisdom. That was the established engineering understanding. And Manzo said, yeah, but what if it doesn't? What if with the right modifications and careful pressure management, you can actually control exactly how those clutch packs engage and release without catastrophic failure? Here's where it gets really interesting from a technical standpoint. The Turbo 400 transmission, which was the absolute gold standard for drag racing applications in 1980, uses hydraulic pressure to engage different clutch packs for each gear selection. In normal operation, the valve body directs transmission fluid to specific clutch packs based entirely on the position of the gear selector. The valve body incorporates safety mechanisms specifically designed to prevent engaging forward and reverse simultaneously, because under normal operating conditions, that would destroy your transmission in roughly 3 seconds of sustained operation. But Manzo recognized something crucial that the conventional wisdom was completely missing. If you could precisely control exactly when and how those clutches engaged, and more critically, how quickly they released, you could use this locked condition as an incredibly effective launch device. The engineering challenge was specific. Figure out how to engage both clutch packs simultaneously without causing immediate catastrophic damage, then release one set instantly and completely when triggered by an electrical signal. The key insight was that brief, simultaneous engagement, measured in seconds rather than minutes, wouldn't necessarily destroy the components if the pressure was managed correctly and the materials were given even minimal time to recover between launches. His solution was elegantly, almost embarrassingly simple when you hear it described. Manzo modified the valve body with an additional drilled passage that would apply hydraulic pressure to the reverse clutch packs while the transmission remained in first gear. A small electric solenoid controlled this additional passage. When the solenoid was energized by electrical current, it opened the passage, applying reverse clutch pressure while simultaneously maintaining forward clutch engagement. When the solenoid was de-energized, it instantly dumped the reverse pressure, releasing the lock and launching the car forward with all that stored converter energy. The first prototype was laughably crude by any modern engineering standard. Manzo drilled and tapped his own valve body by hand using basic shop tools, installed a generic 12-volt solenoid source from an industrial supply catalog that had never seen the inside of a race car, and wired the whole thing to a simple button mounted on his steering wheel. Total cost? About $40 in 1980 money. That's roughly $140 in today's currency. For context that really puts this in perspective, a competitive bracket racing engine in 1980 cost around $15,000. A properly built racing transmission was $3,000. A set of competition slicks was over $1,000. And here was this teenage kid with a $40 modification from a hardware catalog that was about to make all of that expensive, carefully sourced hardware secondary to the reaction time advantage he was about to possess. The first test session was genuinely terrifying for everyone involved. Nobody really knew with certainty what would happen when you locked a transmission solid at full throttle and held it there for several seconds. Would the case split? Would the input shaft twist like a pretzel under the torsional loading? Would the clutch packs weld themselves together from the heat generated? Would the converter implode? These were all legitimate, reasonable engineering concerns that any sensible transmission builder would raise. Manzo did it anyway, because he was 17 years old and had already convinced himself the theory was sound. He pulled up to the staging lights at his local track in Florida, engaged the trans brake by pressing the button, and brought the engine up to his target launch RPM. The car just sat there, engine screaming at 5,500 RPM, tires sitting completely still on the track surface, not moving a single inch. The converter was stalled completely, building tremendous hydraulic multiplication of torque. The entire drivetrain was loaded like an enormous compressed spring, storing potential energy with nowhere to go. Every rotating component was under massive stress, and the car just sat there docile as could be. When he released the button, the result was genuinely spectacular. The car didn't roll forward gradually and then accelerate the way a foot brake launch feels. It literally leaped forward from a dead standstill with shocking violence. the front tires came 6 inches off the ground immediately. The rear tires broke loose simultaneously, sending up a cloud of tire smoke and concrete dust. The acceleration was so violent and instantaneous that Manzo's helmet slammed back hard against the headrest. But more importantly, far more importantly than any of the drama, when they checked the time slip afterward, his reaction time was 0008 seconds. Not 0080, not 0050, 0080, 8 thousandths of a second. Word spread through the Florida bracket racing community like an electrical fire through old wiring. Racers who witnessed Manzo's impossible reaction times immediately assumed the timing system had malfunctioned. How could any human being react in 8 thousandths of a second? The human nervous system simply cannot process visual information that quickly. Research on professional athletes consistently shows a hard floor of around 150 milliseconds for visual reaction time. No amount of practice, no amount of natural talent, no performance supplement changes that biological reality in any meaningful way. Yet here was this kid consistently, run after run, cutting reaction times under 0010. The timing equipment must be broken. That was the only explanation that made sense to the established racers watching. The secret, of course, was that Manzo wasn't reacting at all. Not in the traditional sense. He was anticipating. With the trans brake engaged and the car locked solid, he could release the button when he saw the third amber light illuminate on the Christmas tree, knowing that by the time the electrical signal traveled through the wiring from button to solenoid, the solenoid mechanically released, the hydraulic pressure dumped through the passage, and the clutch packs fully disengaged. The green light would be illuminating right on schedule. He was using the system's own inherent mechanical and electrical delays against itself, timing those delays to perfectly coincide with the countdown sequence. The machine's limitations became the machine's advantage. Within 6 months of that first successful test, Manzo was essentially unbeatable within his local bracket racing scene. He could give opponents a full 1/10 of a second head start based on dial-in adjustments and still win the race because his reaction time advantage was so overwhelming and consistent. Think about what a 1/10 of a second means at 60 miles per hour. That's roughly 8.5 feet of track distance. In a sport where races are routinely decided by thousandths of a second, starting with that kind of built-in advantage was mathematically devastating to every competitor who still relied on foot brake launches. A typical race looked completely demoralizing from the losing side. Both cars would stage, the tree would begin its countdown sequence, and Manzo would be visibly, unmistakably in motion before his opponent's foot had even started the transition from brake to throttle. The opponent would cut what they thought was a solid 0040 reaction time, feel good about the launch, and then watch Manzo's car already pulling away before they'd even completed their launch sequence. In bracket racing, where races are decided by thousandths of a second, having a consistent 50,000th advantage in reaction time was, and there's no other honest way to describe this, like bringing an entirely different category of weapon to the fight. The established racers were absolutely furious. Here's the thing, and this is important context for understanding why the reaction was so visceral. These were people who had spent years, sometimes decades, developing their launch technique. They'd practiced thousands and thousands of repetitions to develop the muscle memory needed for consistent foot brake launches. They'd invested enormous amounts of time, money, and physical effort into becoming elite-level drag racers. Their reaction times were a source of real, legitimate pride, a tangible measure of their skill and dedication to the craft. And now some teenager with a drill press and a $40 solenoid was making their most carefully developed skill essentially irrelevant. They complained loudly and persistently to track officials, claiming the trans brake was cheating, that it was dangerous, that it violated the spirit of what drag racing was supposed to be about. They argued that driver skill should determine outcomes, not electronic gadgets. The old guard wanted it banned immediately and completely, and several local tracks initially did exactly that, prohibiting trans brake use in their bracket classes based on these complaints. But the physics were completely undeniable once you actually examine them honestly. The trans brake wasn't making any car faster in terms of elapsed time. The 10-second car with the trans brake still ran 10 seconds. It was just allowing the driver to launch more consistently and with dramatically better reaction times. The car still had to run its dial in perfectly better reaction times. The driver still had to make accurate judgments about the finish line. The trans brake just eliminated one specific variable, the physical and biological limitation of foot to throttle transition time. That's it. Nothing more, nothing less. Manzo started selling his trans brake kits through classified advertisements in national racing magazines. For $180, you received a modified valve body, a racing solenoid, a wiring harness, and detailed installation instructions written in clear, understandable language. For an additional $50, Manzo would personally modify your existing valve body if you shipped it to him. The orders started coming in as a trickle, then became a steady flow, then turned into an absolute flood. Every bracket racer who lost to a trans brake-equipped car immediately ordered one for themselves. The technology spread through the racing community with the speed and inevitability of a concept whose time had simply come. The technical evolution of the trans brake happened with remarkable speed once the concept proved viable, and the market responded. The first-generation devices that Manzo sold were straightforward on-off systems with no adjustability. You engaged the brake, you released it, and the car launched. Simple, reliable, effective. But racers, being racers, immediately started pushing the boundaries of what the basic design could do. Here's what most people don't realize about how quickly this technology matured once it was out in the world. Within 18 months of Manzo's first commercial kit, there were already third parties manufacturing improved versions with features Manzo hadn't originally considered. One of the first significant discoveries was that different solenoids released at measurably different rates when de-energized. A faster releasing solenoid could shave additional milliseconds off your effective reaction time because the mechanical delay between button release and clutch disengagement was shorter. Racing-specific solenoid manufacturers began developing units with response times measured precisely in milliseconds rather than the imprecise specifications of industrial solenoids. The military aerospace supply chain, which had been developing fast-acting solenoids for fuel injection and hydraulic control systems, suddenly found an unexpected new customer base in drag racing. Then came adjustability, which changed everything about how racers approached launch tuning. Experienced racers discovered quickly that by controlling the rate at which reverse hydraulic pressure released, they could meaningfully tune their launch characteristics for different track conditions, different tire compounds, and different power levels. A slower release rate gave a softer, more progressive launch that was significantly easier on drivetrain components and worked better on slippery track surfaces. A faster release gave more violent, explosive acceleration, but dramatically increased the stress on transmissions, axles, and drive shafts. Variable orifices and adjustable needle valves were incorporated into valve body designs to allow precise control over the dump rate. The valve body modifications themselves became increasingly sophisticated as the technology matured. Early trans brakes drilled a single additional passage to apply reverse pressure, which worked but created uneven loading across the clutch pack. This uneven loading caused accelerated wear on specific friction plates and could lead to premature glazing or failure after relatively few launches. Second-generation designs used multiple precisely sized and positioned passages to distribute hydraulic pressure evenly across all the clutch plates in the pack, dramatically improving durability and consistency. Some designs incorporated check valves specifically to prevent hydraulic pressure spikes during engagement and release. These spikes, caused by fluid momentum when large volumes of hydraulic fluid suddenly change direction, could blow seals, crack valve bodies, or cause inconsistent clutch engagement. The check valves smoothed out the pressure curves, making the system behave more predictably and extending component life significantly. This kind of refinement, borrowed from industrial hydraulic engineering, transformed what started as a hack modification into genuine precision engineering. By 1982, just 2 years after Manzo's first prototype, every serious bracket racer in America had a trans brake or was actively planning to install one. Reaction times that had been considered physically impossible just 24 months earlier were now the baseline minimum for competitive racing. The entire performance landscape had shifted completely and permanently. The racers who adapted quickly maintained their positions at the top of the sport. The racers who resisted either adapted eventually or found themselves consistently losing to competitors who had embraced the new technology without hesitation. This led directly to the next major innovation in bracket racing technology, the delay box. And understanding why delay boxes emerged tells you something profound about how technological progress in motorsport actually works. Here's the thing about trans brakes and reaction times. Once the mechanical limitation of foot to throttle transition was eliminated, The remaining variable in reaction time performance was the human element of deciding precisely when to release the trans brake button relative to the Christmas tree countdown. Different tracks use different tree timing sequences. Different weather conditions could affect track prep and consequently affect optimal launch timing. Even a racer's mood and focus level on a given day could cause variation in when they intuitively release the button. Delay boxes solve this remaining human variable with elegant engineering. The racer would hit the trans brake release button when they saw the second amber light or even the first amber at a predetermined consistent moment in the sequence. The delay box would then hold the electrical circuit open for an exactly programmable duration, measured in milliseconds, before triggering the actual trans brake release. This meant the racer could time their button press to a consistent, easy-to-repeat moment in the tree sequence rather than trying to time the release precisely to the green light. The delay box handled the precise timing mechanically and electronically, with far more consistency than any human brain could achieve under race pressure. Top racers using optimally tuned delay box and trans brake combinations were now consistently cutting reaction times under 0.005 seconds. Some elite bracket racers were hitting perfect 1000 lights, meaning exactly 0.1000 reaction time to the absolute limit of timing system resolution with regularity. The NHRA and IHRA sanctioning bodies found themselves in an impossible position trying to regulate technology that was evolving faster than their rulemaking processes could track. Initially, several sanctioning bodies attempted outright bans on trans brakes in their amateur bracket classes, framing the restriction as a preservation of traditional driver skill. The arguments had a certain nostalgic logic to them. If electronic devices could replace driver technique, what exactly were you measuring in bracket racing anymore? But these bans immediately generated fierce opposition from the racing community. Racers threatened organized boycotts of events that prohibited trans brakes. Manufacturers who would build businesses around the technology lobbied sanctioning bodies aggressively. The genie was completely out of the bottle, and no amount of regulation was going to put it back. The practical resolution was a bifurcated class structure that actually served the sport well in retrospect. Super bracket classes and open classes embraced trans brakes and delay boxes fully, allowing the technology to develop without restriction. Stock classes and super stock classes initially maintained foot brake requirements to preserve their traditional character. This gave racers meaningful choices about which type of competition they preferred. Some genuinely wanted the traditional challenge of foot brake launching and sought out those classes specifically. Others embraced the electronic approach and gravitated toward classes where it was permitted. By 1985, trans brakes were legal in virtually every significant drag racing class except pro stock, where naturally aspirated engines and manual transmissions remained mandatory as class-defining characteristics. Even in classes that had initially resisted, the practical reality of widespread trans brake adoption among competitors made continued prohibition increasingly untenable. You simply couldn't hold a competitive bracket race where some cars had trans brakes and others didn't, because the reaction time disparity would make the competition meaningless. The impact on transmission manufacturing was immediate, profound, and commercially significant. Established transmission builders quickly realized that modifying existing production units as afterthoughts was an inferior approach compared to designing racing transmissions with trans brake functionality incorporated from the very beginning. The clutch pack specifications were completely rethought to handle trans brake use as a primary operating condition rather than an occasional abnormal state. Clutch plates were thickened. Friction material compounds were reformulated for repeated high-temperature trans brake launches rather than normal street driving conditions. Case walls were reinforced at specific stress concentration points identified through failure analysis of early trans brake damage units. Companies including ATI Performance Products, JW Performance Transmissions, and Hughes Performance built substantial, lasting businesses specifically around trans brake optimized racing transmissions. What had started as a teenager drilling holes in a salvage yard valve body became a multi-million-dollar industry segment with sophisticated manufacturing capabilities and dedicated engineering teams. Complete trans brake-ready racing transmissions from established manufacturers could cost $5,000 or more, incorporating exotic friction materials, precision-machined valve bodies, and strengthened cases built to withstand thousands of trans brake launches over a racing career. The torque converter industry experienced an equally profound transformation in response to trans brake technology, and this aspect of the story is genuinely fascinating from an engineering perspective. Here's what most people don't realize about how trans brakes changed converter design requirements. Before trans brakes became widespread, torque converters were designed and optimized around a specific operating assumption. The car would be moving, even slowly, when the converter began loading up. A foot brake launch involves the car bowling slightly, the driver feathering the brake to control wheel spin, and the converter flashing to its rated stall speed during a launch that has some vehicle velocity already built in. Trans brake launches are fundamentally different in ways that matter enormously to converter designers. With the car locked completely motionless by the trans brake, the converter is stalled at essentially zero vehicle velocity for extended periods, sometimes 10 or 15 seconds, while the racer waits for the opposing lane to stage and the tree to count down. During this stall period, the converter is doing enormous work, churning transmission fluid to convert engine torque into hydraulic energy with nowhere to go mechanically. The fluid heats rapidly. The stator, which multiplies torque during stall conditions, is under continuous maximum stress. The friction surfaces inside the converter are operating at conditions they were never originally designed to sustain. Early trans brake racers burned up converters at alarming rates, discovering through expensive trial and error that standard racing converters simply weren't built for the sustained stall conditions that trans brake use demanded. The first response was improved cooling systems. External transmission coolers became mandatory rather than optional on trans brake-equipped cars. Some teams ran dedicated coolers with electric fans that could be activated during staging to prevent fluid from reaching dangerous temperatures before the launch. Fluid temperature gauges became standard cockpit instruments so drivers could monitor thermal conditions in real time. The deeper engineering solution was redesigning the converters themselves for trans brake-specific operating conditions. The stator geometry was optimized for maximum torque multiplication at true zero vehicle velocity rather than the low-speed conditions of foot brake launches. The impeller vane angles were recalculated to efficiently handle sustained stall loads rather than brief transition loads. Turbine designs were modified to survive the shock loading when the trans brake released and the converter suddenly had to transmit full torque output to an accelerating vehicle. Precision balancing became even more critical because the violent launch dynamics amplified any residual imbalance into potentially destructive vibration. The thermal management problem led to material innovations that came directly from aerospace engineering. Aluminum impellers were replaced with steel units on high-performance applications because steel's superior thermal conductivity helped manage heat distribution. Billet steel hubs replaced cast units because the grain structure of forged and machined steel was better suited to the torsional shock loads of trans brake launches. Some converter manufacturers experimented with exotic surface treatments and coatings borrowed from turbine engine manufacturing to improve durability of friction surfaces. The economic democratization that trans brakes enabled in bracket racing is worth examining carefully, because the numbers tell a genuinely remarkable story about how technology reshapes competitive sports. Before the trans brake, becoming genuinely competitive in bracket racing required years of dedicated practice developing launch technique. Natural reflexes and hand-eye coordination provided biological advantages that were simply not available to purchase at any price. Young racers with inherently quick reflexes dominated older competitors regardless of the older racers' superior experience in other aspects of racecraft. This created a form of talent gatekeeping that limited participation and frustrated experienced racers who knew everything about strategy and car preparation but couldn't match a 22-year-old's reflexes. The trans brake eliminated those biological advantages with complete effectiveness. A 60-year-old racer could cut the same 0.005 reaction times as a 20-year-old with the properly tuned trans brake and delay box combination because neither of them was actually reacting to anything. Both were timing their button press to a predetermined moment in the sequence and letting the electronics handle the rest. Physical disabilities that would have prevented effective foot brake racing became entirely irrelevant. Racers with limited mobility in their legs could compete on completely equal terms with elite athletes. The only physical requirement was the ability to press a button, which is an extraordinarily low barrier to participation. The entry barrier that trans brakes removed wasn't just about reflexes either. Consider the time investment required to become competitive with foot brake launches. Elite racers practiced their reaction times constantly, staging and launching hundreds of times between race weekends just to maintain their timing. This required access to a track, available practice time, fuel cost, tire wear cost, and the physical energy to make run after run in a race car. For working adults with jobs and family commitments, Finding the time and resources for that level of practice was genuinely prohibitive. Trans brakes made that investment unnecessary. The consistency came from the device rather than from accumulated physical practice. Bracket racing participation statistics from the mid-1980s reflect this democratization effect clearly. NHRA bracket racing entries at major events roughly doubled between 1980 and 1986, a period that corresponds almost exactly to the widespread adoption of trans brake technology. Track operators across the country reported increased participation in their weekly bracket programs. New racers who might have been discouraged by the skill ceiling imposed by foot brake limitations were willing to enter competition, knowing that with proper equipment and smart driving decisions, they could be competitive from their first season. The psychological transformation in how racers approached competition was equally significant, though harder to quantify with statistics. Before trans brakes, the starting line consumed enormous mental energy during a race. Every racer knew that a poor reaction time could lose a race regardless of everything else they did correctly. This pressure created starting line anxiety that was real, documented, and performance impairing for many competitors. Racers would overthink their launch sequence, second-guess their timing, and frequently either red light in their anxiety to get a good reaction or cut a terrible reaction time by being too cautious. The mental game of the starting line was often more demanding than any other aspect of bracket racing. With trans brakes and delay boxes handling the launch mechanics, that mental bandwidth was freed up for decisions that actually required human judgment. Should you lift early approaching the finish line to prevent breaking out? How much should you compensate for the headwind? Is your opponent going to run under their dial-in? These strategic decisions, which are genuinely the core intellectual challenge of bracket racing, became the primary differentiating skill once starting line reaction times were equalized by technology. Racers who excelled at race strategy and finish line judgment now had their skills properly rewarded rather than being undermined by inferior reaction times. The philosophical dimension of the trans brake's impact extends into territory that motorsport historians rarely explore, but that I find genuinely fascinating. What Manzo did in 1980 represents an early example of a design philosophy that would later become dominant in consumer automotive technology. Instead of trying to improve human performance to match machine capabilities, improve machine performance to eliminate the specific human limitations that create competitive inequality. This is the precise same logic that later produced anti-lock braking systems, traction control, electronic stability management, and launch control systems in production vehicles. Design the machine to compensate for human biological limitations rather than demanding that humans overcome those limitations through practice. The establishment's resistance to trans brakes in 1980 mirrors almost exactly the arguments made against anti-lock brakes in production cars in the late 1970s. Critics argue that ABS removed driver skill from braking performance, that real drivers should learn threshold braking technique, that electronic intervention was cheating physics rather than working with it. The physics don't care about those arguments. A car with ABS stops shorter than a car without it under most real-world conditions, regardless of how skilled the driver is, just as a trans brake racer cuts better reaction times than a foot brake racer regardless of the foot brake racer's practice level. The material science advancement that trans brake adoption drove through the late 1980s and into the 1990s tells its own fascinating engineering story. Early trans brake clutch packs were essentially stock clutch components operating far outside their design parameters. The friction materials used in production and early racing transmissions were engineered for normal shift cycling, not for repeated high-temperature stall launches that loaded the clutches far beyond normal operating stresses. The first generation of trans brake racers discovered through painful and expensive experience that standard clutch materials would glaze over quickly under trans brake use, losing their friction coefficient and causing the transmission to slip under load rather than hold solid. Friction material manufacturers initially approached the trans brake durability problem by simply using harder, more heat-resistant versions of existing compounds. These harder materials improved stall holding capacity but created new problems with coefficient of friction and engagement feel. The harder materials could hold solid at stall, but when the trans brake released and the clutches transitioned from stall to fully engaged forward drive, the engagement harshness increased dramatically. Transmissions equipped with early high-temperature clutch materials would sometimes engage with such violence that input shafts failed or flex plates cracked under the shock loading. The solution came from examining friction material technology from completely different industries. Aerospace engineers working on aircraft braking systems had developed composite friction materials that combined high temperature resistance with more controllable engagement characteristics. Carbon-carbon composite materials, used in Formula One brakes and aircraft stopping systems, offered extraordinary thermal stability with controllable friction coefficients. Racing transmission builders began experimenting with carbon-based friction materials in the early 1990s, and the results were transformative. Carbon clutch packs could withstand trans-brake stall temperatures that would destroy conventional materials while engaging smoothly enough to prevent catastrophic shock loading. The valve body machining technology underwent parallel advancement as CNC machining became accessible to aftermarket manufacturers. Early trans-brake valve bodies were drilled and modified by hand, with passage dimensions and surface finishes varying meaningfully between individual units even when built by the same person following the same procedure. This variation translated directly into variation in trans-brake release characteristics between nominally identical setups. A racer who bought two identical trans-brake kits from the same manufacturer might find the release characteristics measurably different between the two units because hand machining simply couldn't achieve the dimensional consistency that competitive racing demanded. CNC machining eliminated that variation. Hydraulic passage dimensions could be held to tolerances of thousandths of an inch consistently across entire production runs. Surface finishes in critical flow passages could be specified and verified quantitatively rather than assessed subjectively by a machinist's eye and touch. Computational fluid dynamics software, the same technology used to design aircraft fuel systems and industrial hydraulic machinery, was applied to trans-brake valve body design in the mid-1990s to optimize flow path geometry for minimum pressure drop and maximum response speed. What had started as a kid with a hand drill became precision manufacturing requiring $100,000 machine tools and engineering software licenses. Modern trans-brakes, the units being manufactured and sold today, are almost incomprehensibly more sophisticated than Manzo's original $40 prototype, while remaining completely true to his fundamental operating principle. Current high-end trans-brake solenoids from manufacturers like ProTorque and TCI can respond in under 10 milliseconds, roughly 20 times faster than the industrial solenoids in Manzo's first prototype. Multi-stage trans-brake systems allow racers to select different release rates for different track conditions with simple cockpit controls, tuning the launch characteristics in real time between rounds as the track surface evolves throughout a race day. Pulse-width modulated solenoid control borrowed from modern automotive fuel injection technology allows infinitely variable control over clutch pack engagement and release pressure rather than simple on-off switching. A PWM-controlled trans-brake can apply partial reverse pressure to tune the stall load against the converter, optimizing the balance between maximum power buildup and thermal stress on the components. Data logging systems integrated with modern trans-brake controllers record every measurable parameter of every launch, providing racers with detailed telemetry to analyze and optimize their setup between rounds. The safety record of trans-brake-equipped cars deserves honest examination, particularly given how much resistance the technology initially faced on safety grounds. The fear was entirely understandable in 1980. The idea of holding a high-powered race car at full throttle while stationary seemed inherently dangerous. What if the trans-brake released unexpectedly in the staging lanes? What if it failed to release on the start, leaving the engine revving against the stall indefinitely? What if the violent launch loads caused structural failures that created dangerous situations at speed? The actual safety history proved these fears largely unfounded, for important engineering reasons that weren't initially obvious. Trans-brake solenoids are designed to fail in the engaged position, meaning that a loss of electrical power maintains the locked condition rather than triggering an unintended launch. If the wiring fails, if the solenoid burns out, if the battery voltage drops below operating threshold, the trans-brake holds the car stationary rather than releasing it. This fail-safe design characteristic eliminates the most feared failure mode, specifically an uncommanded launch in an inappropriate location. The durability of properly maintained trans-brake systems proved far superior to initial expectations. A quality trans-brake installation in a well-built racing transmission can withstand thousands of launches over multiple seasons without requiring major service beyond normal fluid maintenance and periodic solenoid inspection. The failure modes that do occur, primarily solenoid electrical failures and clutch pack wear, almost universally manifest as the trans-brake failing to engage or failing to hold solid rather than releasing unexpectedly. These failure modes are detectable during staging, before any safety implications arise, because a trans brake that won't hold is immediately obvious when the car begins to creep forward at full throttle. Trans brake technology also contributed meaningfully to safety by eliminating a specific hazard inherent to foot brake launches. During a foot brake launch, there is a brief but real transition period where the driver's foot is moving from brake to throttle and neither control is fully applied. On a sloped starting line, even a minimal backward slope, this transition moment creates a window where the car could potentially roll backward before the throttle takes effect. Trans brake launches eliminate this window entirely. The car is either locked completely stationary or accelerating forward with no intermediate state. The ripple effects of trans brake adoption extended well beyond bracket racing into other motorsport disciplines, each of which adapted the core technology to their specific requirements. Radial tire racing, which grew dramatically in popularity through the 2000s, adopted trans brakes to help manage the unique launch characteristics of small-diameter radial tires with limited mechanical grip. The controlled, consistent loading of a trans brake launch proved far superior to foot brake technique on radial tires because it allowed more precise management of the delicate balance between initial bite and wheel spin. No prep racing. It became a cultural phenomenon through social media and television coverage in the 2010s relies heavily on trans brake technology, precisely because no prep track surfaces are unpredictably variable. When you can't count on consistent track preparation, having at least one completely controllable variable in the launch sequence becomes even more valuable. Trans brakes provide that consistency against the backdrop of surface uncertainty that would otherwise make competitive bracket racing on no-prep surfaces nearly impossible at high power levels. The economic story of what trans brake technology created in the aftermarket racing industry is worth quantifying, because the numbers illustrate just how profoundly a $40 modification can reshape an entire industrial ecosystem. The transmission performance aftermarket in America, according to industry trade publication estimates from the mid-2000s, represented a market exceeding $800 million annually. Trans brake technology and the racing culture it helped accelerate and expand was a meaningful driver of that market's growth from the early 1980s forward. Companies that positioned themselves early as trans brake specialists built durable market positions that persist to this day. The ripple effect into adjacent industries multiplied this economic impact significantly. Clutch manufacturers developed entire racing-specific product lines driven by trans brake requirements. Solenoid manufacturers created dedicated racing divisions. Valve body machining shops that had struggled to find differentiated value propositions discovered that trans brake expertise was a genuinely defensible competitive advantage. Torque converter manufacturers rebuilt significant portions of their engineering and manufacturing capabilities around trans brake-specific requirements. A $40 modification created an industry segment worth hundreds of millions of dollars, which is the kind of entrepreneurial leverage story that business schools should be teaching alongside every technology case study. Frank Manzo's personal story in this context is worth examining with some nuance, because his choices say something important about his character and his relationship to the sport he loved. Here's the thing about Manzo's business approach that most people who tell this story overlook. He could have pursued patent protection for the trans brake concept. The modification was genuinely novel, non-obvious to skilled practitioners, and had clear industrial utility, which are precisely the criteria required for patent protection. A successful patent on trans brake technology, licensed to every transmission builder in America, could potentially have made him a very wealthy man over the following decades. He chose differently. Manzo published detailed technical descriptions of his trans brake design in national racing magazines, making the operating principle freely available to anyone who wanted to replicate it. He sold his kits at prices that covered costs and provided a modest profit rather than at the premium that patent protection would have allowed him to command. When other manufacturers began producing competing trans brake kits, he didn't pursue legal action or attempt to use his first-mover advantage to crush competition. He competed on the merits of his product quality and the reputation he'd built with the racing community. Why? Look, this gets to something fundamental about the culture of drag racing at the grassroots level that outsiders often miss. Manzo wasn't building a business. He was solving a problem that was bothering him personally as a racer, and the commercial opportunity was secondary to that primary motivation. He wanted to race on a starting line where reaction time advantages didn't depend on who happened to be born with quicker reflexes or who had the time and resources to practice foot brake launches for thousands of hours. If sharing his invention openly accelerated the adoption that would level the playing field, that served his actual goal more effectively than patent protection and premium pricing would have. The fact that he built a successful business in the process was a consequence of solving a real problem well, not the primary objective. This philosophy of open technical knowledge sharing, which seems almost quixotic in the context of modern intellectual property culture, earned Manzo a quality of respect in the racing community that money genuinely cannot purchase. Racers who initially despised the transbrake for what it did to their competitive advantages came to respect Manzo personally once they understood that he hadn't developed the technology to exploit them commercially. He developed it because he was a racer who had a better idea, and then he shared it because he was a racer who wanted fair competition. The legacy of the transbrake in drag racing history deserves explicit articulation, because I think it's easy to get lost in the technical details and miss the larger significance of what this invention actually accomplished. Consider what the state of bracket racing looked like in 1979 versus 1985, just 6 years after Manzo began developing his prototype. In 1979, bracket racing was competitive but stratified. Elite racers with exceptional natural reflexes and years of practice dominated their classes. Entry was open to everyone theoretically, but practical competitiveness at the top level required biological gifts that couldn't be trained into existence. Older racers, physically limited racers, and racers without the time for extensive practice were structurally disadvantaged regardless of their knowledge, strategic thinking, or mechanical preparation. By 1985, that stratification was largely erased. A racer with a well-prepared car, a properly installed transbrake and delay box, and a sound understanding of bracket racing strategy could be competitive at the national level regardless of their age, their natural reflexes, or how many hours they had available for practice sessions. The technology had redistributed the competitive premium from biological gifts to accessible skills and knowledge that any motivated competitor could develop. This is democratization in the truest sense, not just making something cheaper or easier, but actually removing structural barriers that prevented capable people from competing effectively. The lessons that Manzo's transbrake teaches about innovation in motorsport are applicable well beyond drag racing. First, the most impactful innovations often come from users of a technology rather than from its manufacturers. Manzo wasn't a transmission engineer. He was a racer who understood his problem better than any engineer who wasn't competing at his level could. His intimate knowledge of exactly how and why foot brake launches were limited gave him insight that professional transmission designers simply didn't have motivation to develop. This pattern of users innovating more effectively than manufacturers because users understand the problem more viscerally repeats throughout motorsport history. Second, simple solutions to well-understood problems are almost always more robust and adaptable than complex solutions to imprecisely understood problems. Manzo's transbrake was conceptually simple enough that a competent mechanic could understand it completely after a 10-minute explanation. The implementation required skill and attention to detail, but the principle was transparent. This conceptual accessibility contributed directly to the speed of adoption across the racing community. When racers understood why it worked, they trusted it and embraced it. Mysterious black box solutions generate skepticism. Elegant, simple solutions generate enthusiasm. Third, and perhaps most importantly, technology that genuinely expands access and participation in the sport tends to grow the sport in ways that benefit everyone, including the established participants who initially resist it. The veteran racers who fought trans brakes in 1980 were competing in a sport that had far fewer participants than the sport they were competing in by 1990. More participants meant more entry fees at local tracks, which meant better track maintenance and facilities. More participants meant larger purses at major events as sanctioning bodies had more revenue to distribute. More participants meant more manufacturers investing in performance products, which meant better and more affordable equipment for everyone. The democratization that trans brakes enable grew the entire ecosystem, not just the portion occupied by new entrants. Picture yourself standing at a drag strip today, watching a bracket race unfold. Two cars roll into the staging beams with practiced efficiency. One of them, maybe both, will sit there for a moment with the engine revving higher than sounds comfortable. The car completely motionless despite obvious power input, the rear tires pressing hard against the track surface but not moving. That motionless moment, engine at full power, car going nowhere, is Frank Manzo's legacy in living, breathing mechanical form. That's a 17-year-old kid's $40 idea, refined over 4 decades by thousands of racers and engineers, still operating on exactly the same principle it did the first time Manzo pulled up to a starting line in Florida and showed the establishment what a genuinely new idea looked like. The next time someone tells you that all the good ideas in motorsport have already been found, that there's nothing left to invent, that the big breakthroughs require big budgets and engineering teams and research facilities, remember Frank Manzo. Remember a teenager with a drill press, a hardware store solenoid, and the stubborn conviction that losing races because of biological limitations was a problem worth solving. Remember that the most important innovations in drag racing history didn't come from Detroit engineering departments or aerospace contractors. They came from racers who were sick of losing and smart enough to think differently about why they were losing. What's your favorite piece of grassroots racing innovation? What's the clever, unexpected modification that changed your local racing scene the way the trans brake changed drag racing nationally? Drop a comment below because I genuinely want to know about the creative engineering happening at tracks around the country that never makes it into the mainstream motorsport press. And if this kind of deep dive into the overlooked history and engineering of motorsport is something you want more of, subscribe to Legacy Motoring because we have a lot more stories like this one waiting to be told. And most of them involve ordinary people doing extraordinary things with limited budgets and unlimited creativity.